inverse functions. So let's begin our discussion with the graph of sine x. This function, is it a one-to-one function? And how would you know if it is or not? To determine if a function is one-to-one, you need to see if it passes the horizontal line test. And the sine function does not pass the horizontal line test. The curve touches the horizontal line multiple times. If it touches it only once, then it passes the horizontal line test. So because the sine function does not pass the horizontal line test, it's not one-to-one, which means there is no inverse function of the sine function. If you try to draw an inverse function of it, it will look something like this. As you can see, this is not a function because it doesn't pass the vertical line test. The vertical line test tells you if a curve is a function or not. The horizontal line test tells you if it's a one-to-one function, and it tells you if the inverse is a function. So there is no inverse of a sine function. Now what if we restricted the sine function? So for example, here's the original sine wave. But let's say if we restricted it in this region, that is from negative pi over 2 to pi over 2, where the y value changes from negative 1 to 1. So let's redraw the restricted sine function. So this is the restricted sine function from negative pi over 2 to pi over 2. Now this graph passes the horizontal line test, which means it's one-to-one and the inverse function exists. So let's draw the inverse function of the restricted sine function. So this is y equals sine x, where x ranges from negative pi over 2 to pi over 2. The inverse sine function is going to look like this. It's a reflection across the line y equals x. So if you were to draw the line y equals x, which is this line here, all you need to do is draw the reflection around that line. Now my drawing's not perfect, but this is how the inverse sine function looks like. The domain of the restricted sine function is from negative pi over 2 to pi over 2. For the inverse function, the domain is the same as the range. So the range is now from negative pi over 2 to pi over 2. So the x and y values have switched. As you can see, pi over 2 and negative pi over 2 were x values. Now they're y values as you deal with the inverse function. Now the y values for the sine function, it varied from 1 and negative 1. So now those values are the x values, negative 1 to 1. So the range of the sine function, which is negative 1 to 1, now becomes the domain of the inverse sine function, or the arc sine function, which is negative 1 to 1. So now you know the domain and range of the arc sine function, and you have its graph as well. Now let's talk about the inverse cosine function. So here's the graph of cosine x. What we're going to do is we're going to restrict it from 0 to pi, which is only this region here. So let's draw the restricted function. So it's from 0 to pi, and it varies from negative 1 to 1. So the domain of the restricted cosine function is 0 to pi, as you can see, and the range is from negative 1 to 1. So we have to restrict it because we want it to pass the horizontal line test. We need to make it a one-to-one function so that the inverse function will exist. So keep in mind, the inverse function exists for the restricted cosine function, not for the regular cosine function, because that's not one-to-one. So now let's draw the inverse cosine function. cosine of 0 is 1, so we have that point, and cosine of pi is negative 1. So notice that the y values are now x values when dealing with the inverse cosine function. And we said cosine of 0 is 1, cosine of pi is negative 1, cosine of pi over 2 is 0, which is in the middle. And so to graph it, it's going to look something like this. So the domain will become the range of this function, which is 0 to pi. And the range turns into the domain, which is negative 1 to 1, as we can see here. So that is the graph of the inverse cosine of x. This is it. Now let's go over the graph of tangent. We know that tangent has a vertical asymptote at pi over 2 and at negative pi over 2. And so here's the generic shape. It's an increasing function that looks like this. Now we can draw another period of the tangent function. And it looks like that. But notice that if we draw another period, it no longer passes the horizontal line test. It is no longer a one-to-one function, as you can see. However, if we just use one period, then this function does pass the horizontal line test, which means that there is an inverse function for this graph alone. So I'm going to redraw a smaller version of the arctangent function, which looks like this. So the restricted domain is in between the two vertical asymptotes, which are located at negative pi over 2 and positive pi over 2. So the domain for this restricted tangent function is negative pi over 2 to pi over 2. But notice that it doesn't have a restricted range. The range is from negative infinity to infinity. Now let's draw the inverse function. So instead of having vertical asymptotes, the inverse function will have horizontal asymptotes. Since these are x values, they will become y values. So this is the asymptote at y equals negative pi over 2, and we have another horizontal asymptote at y equals positive pi over 2. And then the graph is going to look like this. Okay, let me do that a little bit better. So the domain is now the range. The range is from negative pi over 2 to pi over 2. And the range switches to the domain, which is all row numbers, negative infinity to infinity. It starts all the way from the left and it ends all the way to the right. So this is the graph of the inverse tangent of x function.
So hopefully by now you have filled out the chart over here. This chart was described in the first part of this video. If you haven't done that, please make sure you've done that now. Also, I want to point out over here in the top left just some notation variations. The video thus far has used the notation here on the right, sine to the negative first, or sine inverse of x, cosine inverse of x, tan inverse of x. But you could also write those same functions as arc sine, arc cosine, arc tangent. I just want to make sure that you guys are aware that those notations are interchangeable and they get used pretty much the same amount of time. And then the last thing I want to point out here is that we're being asked to express our answers in radians. Really important that you answer the problem in the correct angle measurements. Inverse trig can be done in radians or in degrees. So I just want to make sure that I'm pointing that out to you guys. This particular worksheet, we're going to be answering in radians. So let's go ahead and get started. This first problem here is sine inverse of root 2 over 2. So what we're being asked to find is where is sine root 2 over 2? Sine is positive in the first and second quadrants, but if we're following our range restrictions, we're specifically just going to be looking at quadrant number 1. As a reminder, sine is the y value in the ordered pair, so we're going to be looking at this ordered pair right here, and that answer in radians is pi over 4. So sine inverse is pi over 4. On to the next problem. Sine inverse of negative root 2 over 2. This time we're going to be looking at the third and fourth quadrants. Specifically the fourth quadrant because we know that the range restriction is from negative pi over 2 to pi over 2. Hopefully you guys realize that we're looking at this ordered pair right here, this 7 pi over 4. But 7 pi over 4 is not within that range restriction. We actually need to be going backwards towards this angle. And when we go backwards, as a reminder, angles in standard position where we rotate clockwise end up with a negative angle measure. So we're not going to be writing down 7 pi over 4, but we're actually going to be writing down negative pi over 4. As a reminder, in order to get that, you would do 7 pi over 4 minus 2 pi to get that negative pi over 4. Okay, on to our next problem. Sine inverse of negative 1. Where is sine negative 1? Well, sine and cosine are positive and negative ones at the quadrantal values, or the values where the angles would have a terminal side at the quadrant lines or the axes. At 0, since we're talking about sine, we're looking at the y value. So sine at 0 is 0. That's not going to work. I'm going up here to sine at pi over 2. The sine value is positive 1, so that's not going to work either. We actually have to go down here to this 3 pi over 2 to get that sine of negative 1. But remember, we have to go backwards towards 3 pi over 2. So sine inverse of negative 1 is negative pi over 2. Oops. Then on to our last sine value, sine problem. Sine inverse of 2. Where is sine 2? Remember, the input value is our domain. Since 2 does not fall within the domain values of our inverse sine function, we actually cannot answer this problem. So when our input values don't fall in the domain, we actually describe this as being undefined. And again, that's because 2, or the input value, does not fall in our sine inverse domain, which is negative 1 to positive 1. So now that we've practiced with sine, let's go ahead and look at our other two functions. Next, I'd like to focus on cosine. A cosine's a little bit different than sine in the fact that we're looking at different quadrants. If you look back up at the chart at the top, we're looking at quadrant 1 and quadrant 2. So this first problem, cosine inverse of negative root 2 over 2, where is cosine negative root 2 over 2? We're going to be looking at the second quadrant here. Cosine is the x value. So where is x negative root 2 over 2? We're looking at this ordered pair right here, which is 3 pi over 4. And then cosine inverse of negative 1/2. Where is cosine negative 1/2? We're still looking at that second quadrant here. Which ordered pair or which angle measure has an ordered pair that has an x value of negative 1/2? That would be 2 pi over 3. So cosine inverse of negative is 2 pi over 3. So cosine is nice because we don't have to worry about going backwards at all. We're just dealing with the first and the second quadrant. Now, last but not least, we have a couple of tangent problems here. Tangent has the same range restrictions as sine. So we're going to be looking at the first quadrant and back into the fourth. But we have to remind ourselves that tangent is y over x. So we're not going to be looking at a specific ordered pair or part of the ordered pair on the unit circle, we're going to be looking at the ratio of the y value over the x value. So this first problem, tan inverse of root 3 over 3, where is that ratio of y over x root 3 over 3? Tangent's going to be positive up here in the first quadrant. So I know that I'm going to be dealing with one of these three ordered pairs, pi over 6, pi over 4, or pi over 3. Pi over 4 we can remove from our possibilities because we have the same x and y value. And when you divide the same the same value by itself, you end up with 1. So we're either going to be dealing with pi over 6 or pi over 3. In this case, we're dealing with pi over 6, and let me show you why. At pi over 6, the y value is 1/2, and we're going to divide that by the x value of root 3 over 2. The common denominators cancel, and we end up with 1 over root 3. And then as a reminder, we have to rationalize in AET honors. So we end up here with root 3 over 3. So that is a little bit of work here to show you why tangent inverse of root 3 over 3 is pi. Similarly, if we were to look at tangent inverse of root 3, we're going to be, again, looking at that first quadrant. We know that it's not going to be pi over 6 because the tangent at pi over 6 is not going to be the same value. There's not going to be two values at the same time. We know pi over 4 is going to be 1 because of that matching ordered pair. So by default, we're left with pi over 3, and that is the answer here. Again, showing you why that is the case. The y value at pi over 3 is root 3 over 2. And we're going to divide that by the x value, which is 1/2. The common denominators cancel, and we're left with root 3 over 1, or just root 3.